Okay. In the last class, we have discussed that why do we need transmission and distribution system. Then the answer we got was to transport the electrical energy from generator side to consumer end. Then we had the query that if it is needed to transport the electrical energy from generator side to consumer end, and we know that the electricity is neither available naturally, that is, we do not have any availability of electrical energy in direct form, nor it is utilized in the same form, then why this intermediate form is needed? And we tried to explore some regions, and we found that there are not only a single reason, but there is a list of reasons because of which the electrical energy and its transportation has become so much popular. So one of the reason is that is some form of energy. If we transport it in direct form, their associated transportation cost is higher relative to if we generate the electricity at the same point, at the sending in point, and then convert back at the receiving in point to the form of energy we like, then the associated cost in the second option is lesser than the first one. But this is not true for all the cases. This maybe the example where the energy is bulky, like say for example coal or petroleum product like petroleum oil or diesel or something like that. Then there are another reason which is very important, that is unavoidable reason, that is some form of energy cannot be transported at all. For example, we have discussed that like hydro energy. Hydro we can generate only where there is a head available, and as you might know that to construct the dam also we minimize the cost for the dam. We try to make the dam near the neck of the river. This is also not only true for the hydro, but maybe for example wind. Wind, the energy generated from the wind energy is proportional to the cube of the wind velocity. So this energy from the wind can be economically practically generated only if the speed of the wind is something higher than a benchmark level, minimum level, and that is not available everywhere. So that's why even we cannot generate the wind energy at our home itself in the mass. Like, but if you go around the seashore or something where the wind can blow from the far, then its speed is higher, and then it can be conveniently or economically generated. At the same times, we also discussed that, like for example, nuclear energy, we cannot use it in direct form near the highly densely populated areas because of the risk available, mainly with its waste. Hello? Why? Yes. Mainly due to its waste disposal. Then, last but not the least, we also discussed that the electrical energy has made us in modern age the much more convenient, like net and computer and everything, and it's also fast, that is electrical switching on off is very relatively fast with respect to the mechanical or other type of system. Then we also discuss that yes, okay, so we generate the like at the coal pit, coal transportation cost is higher. So generate the electricity at the coal pit and transport it to the utilization point and use it whatever is the electricity available from that generator. Then from next another coal pit again generate there and use for the other consumers. But in general we do not do that, but what we do is we interconnect this all possible generators or available generators together to form a like a grid. Then we also discussed that why we need the several generators and the loads should be interconnected. And we discussed that, yes, if we interconnect all these, then there is a opportunity to improve the reliability. See, this is a very diplomatic sentence. I have not said directly that it improves the reliability, but I said that we have the opportunity to improve the reliability. What does it mean? What's the difference between the two? If you just say that improve the reliability, means it is whatever may be the condition, just interconnect it, it improves the reliability. But if we say that opportunity to improve the reliability, this means that if we interconnect, then we have the opportunity to improve the reliability, provided some other conditions should be met. And that conditions we have discussed, that we should have sufficient reserve margin. What does it mean by the reliability improvement is, in case we have the failure of some generators or lines, then other generators or lines can immediately share the load that was shared previously by the unit which have been failed. But for that purpose, we must have sufficient reserve margin. For example, in our case, like in Nepal, we have around the today around 1500 megawatt of demand. So now, if the available generation is also 1500 megawatt, you can imagine, and you have some failure of some line or some generator, then we cannot meet that. But if we have a generation capacity of, say, available generation capacity of 1800 megawatt, and the demand is 1500 megawatt, and now we have a failure of 1 unit, say, of 100 megawatt or something, then yes, we can, provided again our transmission capability should allow it. So reliability can be improved, but with reserved capacity of the generation as well as transmission. Then we also discussed that, yes, the very great advantage we can achieve by interconnecting the several generators and demand together is we can exploit the demand diversity, because the util- users or consumers of the electricity have used the electricity, as I have told you last class also, to accomplish some tasks, some different tasks, and these tasks varies over the wide range. Like some people is using the electricity, like in our campus we use the electricity for teaching lab purpose, or in hostel or something. That means in office they use 10 to 5, or some industrial may operate 24 hours. Some residential customers, they operate usually in the evening, they have the maximum demand. So the demand of all different consumers are occurring at different time. So if we aid all these, then the addition of all their peak demand not needed. Just a particular instant of time, just add their instantaneous demand, and in that case, some may operate at peak, some may operate at their middle of the peak, or some may be at the off peak. So in that case, we can reduce the generation capacity as well as the transmission capacity due to the diverse nature of the utilization of the electrical energy. Then we also discussed that today, which is very important, then renewable energy is becoming very popular, and their interconnection to the grids are increasing day by day. So, but it has the problem of intermittency. That means it is a kind of unregulated generators. So, from, like, for example, wind or solar, we can get the electricity only if we have a sufficient wind speed, or we have a ample solar radiation available. And in that case, but if it is not, the demand consumption we cannot stop. So for that means, if for case of the renewable energy, we must have some backup energy from the conventional sources, and if we interconnect these conventional source together with the renewable energy, we can avoid this intermittency problem of the renewable energy. Then we discussed that, yes, we have also the operational flexibility. Whether it is in deregulated, I had given you an example of the deregulated electricity market in last time, but it's also true in the regulated electrical energy market. So, say, I hope that you might, some of you might have taken the elective course in electrical energy system management, I guess the name. So in that course you might have familiar with one terminology called economic load dispatch. What does it mean by the economic load dispatch? That means if you have, say, the you within the thermal unit itself, like thermal generator 1 2 to say 50 number of thermal generators, and you have a fixed demand at a particular instant of time, then there it is not necessary that you generate and say that, of course, the generation available capacity of all these 50 generators is greater than the total demand of that instant. Then it might be, the one case might be that make the some units off and some unit on just to meet the demand. Other, that means share some generation by each and every 50 units to meet the demand. And it has been proved, I cannot prove it just now, that there is a opportunity to grasp the minimum running cost. And this economic load dispatch mainly is important for those generators where the running costs are high, like the thermal or like coal based or diesel based, all thermal generators basically. So that means if you have several generators available, and then to meet a particular instant demand, there may be a most economical scheduling among the different generators to meet that particular demand, to minimize the mm, running cost at that instant of time. Then we may have the operational flexibility among the different sources. Say, for example, we have thermal and hydro. Then what you can do is, like PROR or something like that. We have, or hydro, so, and wind. Then we may to use that hydro. We can store it if we cannot use it. So use other energy and keep some. This is called hydrothermal scheduling, or these days coming together with the renewable energies as well. So within the hydro itself, we may have, like we say that during the daytime we can not use the say Kaligandaki A or Marsyangdi, because these are the peaking run of the river type of generators. So during the daytime when the demands are less, we share the demand by the other ROR generators, and during the evening peak when the demand is very high, then operate those Kaligandaki or Masyangdi, so PROR. And storage, as you know, that in our case we have the Kulekhani 1 2 and 3 by now. And these are used usually when the river flow is less. So that is the seasonal operational flexibility is also there if we have interconnection of several generators. Then the most important part we discussed, that why we connect the several generators, even the above advantages were not there, to have a minimum loading effect. That is, what the loading effect mainly is: the fluctuation of voltage and frequency with varying demand. So if the demand is lower, usually the voltage and frequency are higher, and if the demand is high, then vice versa. That is, both the voltage and frequency tends to decrease. But this effect relatively is much lower if you share that demand by interconnecting the several generators together with respect to the a single isolated generator that we have proved last time as well. Then at the last we were discussing that even within the power, what is the power delivery system? Power delivery system is in fact the lines or links which interconnect the the sources to customers. But we discussed that in the last time also, that it is not that all the components in the power delivery system carries the same power. So at some points, these lines may diverge. I had given you the example of tree. Like initially, it is a very thick and single one. Later on, there are branches and sub branches, and the job of the different branches of a tree to to supply the food which is getting by the roots to the leaves of the tree, and different branches carries different leaves, so that's why it should have the different capacity, and the same applies in the transmission links as well. Then at the last, we were at this point, we were discussing that when the a line carries more power, high power, then it should operate at high voltage than with respect to the lines carrying lesser amount of power. And why? We were here, and we, in fact, in the middle, we had to stop. So I restart from that point where we left. But before that, I will restart. I will drive that equation again and continue. But before that, I will give you some time if you have any queries or need further explanation what we had discussed so far. Do you have any query? No? So then I will
सर
continue. Yes.
सर क्वेसन त छैन तर साउन्ड चाहिँ अलिकति डिस्टर्ब आइरहेको छ
आइरहेछ त्यस्तो
मेरोमा मात्र हो कि सबैको हो
होइन आएको छैन हजुर ठिकै छ मेरोमा त
क्लियर छ
ठिक छ ठिक छ
के छ
प्रवीणले
ठिक
पनि
छ
डिस्टर्ब भएको छ
क्लियर नै छ
क्लियर छ है ठिक छ सर कन्टिन्यू गरौँ
Okay. Okay. So what we were discussing that now suppose we have somewhere we have a source and we have a load at this point, and we have to transmit or of the power or energy. In fact, as you know that the power is the instantaneous energy itself. So at a particular instant of time, we need to transmit the power. Now, that means we have to transport P amount of power from this sending in point to the receiving in point, and suppose that the distance from here to here is L. Then right now we do not know what's the current flowing, what's the voltage, and something like that, because P is related with the current. But this is our main job. That means we have to transmit P amount of power over a L distance. So in the design, we should choose the voltage, the conductor size, and several things one by one, that will proceed one by one. But right now, that means why the current flows through this line is because of this power we have to deliver from this point to this point, and is correlated this P. If we say that this line is say three phase line, then this P is correlated with the voltage and current by this expression, that is P equal to, this is a very famous equation you might have studied in the first year itself. P is equal to root 3 bi cos phi, where this B is the line to line voltage and I is the line currents, and cos phi, I know that you know that this is called power factor. Then if we just interested to find out how much is the loss per conductor, so in this equation P loss per conductor per conductor per conductor is I square into R, right? Now from this expression, this we can get P is equal to I is equal to P divided by root 3 V cos phi. Substitute this, you'll get P square upon 3 V square cos square phi into R. Then this is loss per conductor. In the three-phase line, you know that we have 3 lines. So that's why the total P loss in the line is 3 times of P square R upon 3 V square cos square phi. So that means this 3 gets cancelled. Now, where is this R coming from? Why this R is coming from? R is the resistance of the total length of the conductor from here to here. And this R is related by relate, expressed as rho L by A, where rho is the resistivity of the conducting material. So what material we use, we will discuss later on, depend merits and demerits of the different materials and why we use some specific materials for the conductors. This L is the total length from here to here, and this A is the cross-sectional area of the conductor. So each and everything for during the design is a variable. So consider it specifically. So if we replace this R again by with this and this expression, then our power loss expressions P loss is coming to be P square upon V square cos square phi into rho L by A. We were here. In this expression, so till now, just discuss that which are the quantities that could vary over wider range and which are the quantities vary over the narrow range. So, for example, P, what do we expect? Is expect in the different cases, we are considering not only a single cases, among several cases. The P in somewhere we may need it just to transport 1 megawatt of power, or maybe somewhere just say 50 kilowatt, and sometimes we may need to transport thousands megawatt. So that means this P varies over the wide range. This L also sometimes, yes, do you have any query? This L, sometimes we need to carry only the power over only a kilometer or few meters, and sometimes you may have to transport the power up to thousands of kilometers. So that means this P, this L varies over the wide range. Whereas if we talk about this power factor, say cos phi, how much cos phi will vary? If for different types of load, as you know, that it varies around in a practical cases from 0.7 to 1, and this 0.7 is for the usually is the lowest for the case of induction motors, and 1 is the resistive load as well. But at the same time, so we also what we do is so the variation here is less, first point. Second, the reactive, this cos phi can be improved by reactive power compensation, and that can be this not necessarily require the some energy. So that means, for example, real power, why we should generate at the coal pit or the where the head is available, because it needs real energy as an input, some form of energy. But the reactive power is not associated with the energy. That's why we do not need the energy resources, and that's why we can generate it anywhere. And you know that the very popular method of improving the reactive power is capacitor placement. And usually what is done is, say, just take an example. Suppose we have a line from here to here, and then one line is going here, another line is going here, and then we have one line going here, and we have a demand here which is of very low reactive power. We have a load at this point which has the power factor, very low power factor of say 0.7, power factor of 0.7 at this point. Now, if we say that we supply this reactive power from here itself, this associated with a reactive, some reactive power P and Q, as you know that lower the power factor means higher the reactive power Q. So if we supply this reactive power will flow from here. It will also flow from this path. It will also flow from this path. It will also flow from this path. So in all this line throughout from here to here, it will flow and it will create the losses in all the lines associated with this. But if I say I generate the reactive power, say for example at this point, I generate now the reactive power at this point. Now what will happen? This reactive power no need to flow from this line, only this reactive power will flow from this to this. Similarly, if instead of here, I do not generate here, I like to generate here. If I generate here, then the reactive power will flow only from here to here. Even at this point, no reactive power flow will be there. So the loss can be minimized here and minimized here. So this is a trend that as far as possible, the reactive power should be generated as near as to the load. Yes, for each and every load, we may not be able to generate because the number of capacitor placement will be too high, too many. But as far as possible, we should. So what I mean is near the sources, as we approaches from the consumer ends towards the sources, the power factor is in general is higher and higher. So one thing is this power factor to not vary as in the range of varying the P or L. Secondly, it varies in the it is higher. Then so that's why, and this rho is depends upon the material property, as I have told you, as you know by now that there are only few conductors we are using for electrical purpose. Though there are so many conducting materials, but only few like copper or aluminum. The two are most popular. Others like silver is very costly. We cannot use it, and some other like iron. This has a very high resistivity. Therefore, also we do not use it. So most popular is only two, and there are advantage and disadvantage. This we will discuss when we discuss the conductor selection in our coming days. Uh, and there I will justify you is especially for overhead line, the aluminum material is the highest advantage in relative to others. So that means if the material is fixed, this rho is also fixed. So what I can summarize is how I can summarize is that the power loss is equal to P square over L upon V square into A into rho by cos square phi. Why I have written like this is I'm trying to separate the parts which are almost fixed. This is almost fixed, not varying wide range. Whereas for these parameters P, L could vary very high. And last time also I told you that just saying the 10 megawatt power loss or 20 megawatt power loss is not much more meaningful because 10 megawatt power loss from how much power? That is important. For that purpose, usually we express the power loss in terms of percentage power loss. So if we write the percentage power loss, the percentage power loss is P loss upon P, of course, the multiplied by 100. So, but it may not be for right now, it may not be necessary to derive it, but just per unit or percentage, as you know, is same. So we can write that this is PL by V square into A and into some constant. Okay, here, very important, I have mentioned you last time also that if you just see this expression, not only the total power loss is varying proportional to P and or L or multiple of power to be transmitted and distance to be transmitted, but the percentage power loss itself varies the proportional to the product of the power to be transmitted. And so what does it mean? That if everything remaining the same, like voltage you do not vary, for everywhere you are going to use the same voltage, everywhere you are going to use the same size of the conductor and same material, then if you have a 10% of loss for the 10 megawatt for 10 kilometer to be transmitted, then for 100 megawatt for the 10 kilometer, the losses will be multiplied by 10 times, that is 100%. So loss will be much more higher. So what is usually our trend is, you may know that, like suppose you are transmitting 1 megawatt, even your loss will be 5%, we may not be that much worried. But if you're transmitting 100 megawatt, in that case, even you desire that, yes, this 5% itself means 5 megawatt loss. So it's too big. So we try to minimize it. But right now, just to get and develop an idea, suppose that we want that whatever may be the power to be transmitted, we want a fixed percent of losses. I have hinted you what I mean. I mean that higher the power you transmit, usually we want that the percentage power loss is lower. Just to develop an idea, right now, you assume that, okay, whatever may be the power to be transmitted, we are assuming that we cannot go beyond a percentage power loss. So for a fixed percentage power loss, fixed percentage power loss, what is required is, what is required is this this quantity should be constant. So what does it mean? That if PL, product of P and L increases, also the voltage square upon A should must be increased, isn't it? So higher the power or L, V square and A multiply, where V is the voltage. That means more is your real power to be transmitted, or and whatever may be the distance to be transmitted, the product of voltage and the conductor size should also be higher. So just make correlate that what if we choose, say for example, voltage, then what should be the size of the conductor? Or if we choose the size of the conductor, then what should be the voltage? To that, for that case, for again we are writing for fixed percentage of loss, we can say that the correlation for the size of the conductor A is equal to, I'm writing missing some steps. I hope that you might catch it. A is equal to P L by V square and some constant, say K1, right? So what does it mean? That Now, suppose you know the value of P to be transmitted, and also you know the distance to be transported. This is fixed. Then, if we try to get an idea of how the size of the conductor varies with respect to the voltage, if we plot it here, and I write over here the cross-sectional area of the requirement of the conductor, then for a fixed P and L, the nature of the curve correlating the cross-sectional area and the voltage is the size of the conductor A is proportional to, universally proportional to the square of the voltage for given or fixed P and L. So it looks like this. So what does it mean? Okay, what this cross-sectional area, why we are focusing on this cross-sectional area? Because higher is the cross-sectional area of the conductor, conductor cost is higher. You know that transmission line basically consists of only two costs. You know, one is, and the major cost is cost of conductor. So here we have an idea that as we go on increasing the voltage, the cost of conductor goes on reducing. Then the natural question arises that again this does not justify that there should be a different voltage. Why not we always go for maximum voltage? Because if we say whatever may be the power or distance to be transmitted, if we go higher and higher voltage, then the cost of conductor will be lesser. But this is the only a part of the story. So as if I write it like as an conductor cost, then as you increase, there is another cost also associated with the transmission line. The two basic costs I have told you, just I have mentioned you one. One is conductor cost, and second is insulator cost. So insulator cost roughly, as you know that if you have 11 kV system and you go for 33 kV system, the insulator cost is very roughly proportional to the voltage level. That is, for 33 kV system, you may require 3 times more insulator. So, or something like this. Okay. So that I have tried to explain you in the next slide. So these expressions we have just now we had derived it, and we can say that the cost of conductor per unit length for fixed P and L is look like this. So for a given amount of power to be transmitted over a given distance, the cost of conductor is inversely proportional to the square of the voltage. I hope that up to this much is clear. Then why not all lines are at high voltage? That I have tried to explain you. So the line cost consists of mainly two costs. One is conductor cost and another is insulator cost. So cost of conductor, as we go on increasing the voltage, again I am repeating several times, for a given amount of power to be transmitted over given distance, that is P and L, we are not varying. For given P and L, the cost of conductor is going on decreasing as we go on increasing the voltage level. However, the cost of insulator goes on increasing as the voltage level goes on increasing. So, there, if we just try to get the total cost curve, so total cost, say for example, if we transmit that P over the given L distance, then if we choose, say for example, this voltage, if we choose this voltage, then the total cost is this plus this. If we choose this voltage, then the total cost is this plus this. or if I choose this voltage, then the cost is this and this. So if we try to plot this total cost curve, then you will find very interestingly, it is looks like this. What does this mean? This means that for a give, and of course, I again and again I am repeating, this curve till now we are plotting just to correlating the cross-sectional area and voltage level or associated cost for a fixed P and L. So we are not varying the P and L. So for a given amount of power to be transmitted over given distance, there is a condition where the minimum total cost is associated, and for this is for a given voltage. So this in formal language we can write it or we can explain it as there is a most economical voltage for a given amount of power to be transmitted over a given distance. Now what if we go on increasing the, that is the next question. So that means just first one, and we will find out this most economical voltage maybe in next class exactly what will be the most economical voltage. But right now just you should understand that for a given amount of power to be transmitted over a given distance, there is a most economical voltage. That means if you use voltage lesser than that or higher than that, in both the cases the total cost will be higher than if you choose that voltage. How this voltage is chosen, I will explain it to you later. Okay, then right now till now we were discussing just for a given amount of power to be transmitted over a given distance. Now think if the P and L varies just in this curve itself or even in previous cases, just I will go back first and then come again. Okay, so this expressions, this is the expression and this is the curve for a given P and L. Now if I say that now I change this PL, previously this was at P1 and L1. Now in next case say that okay, L is, whenever I'm saying that P1 L1 product, one thing you remember that either we change the P or the L or both. In both all the three cases the product P and L is changing, right? So now we say that we have three conditions: P1 L1, P2 L2 and P3 L3. So different scenario. Yes, this itself may not be easier for the explanation. So we must have some idea that among this P1 L1, P2 L2, which is bigger and which is smaller. So suppose that P2 L2 is bigger than P1 L1, and, and similarly the P3 L3 is bigger than P1 L1. So if this curve is for P1 L1, what will be the curve for P2 L2 just from this expression? This is the cross-sectional area of the conductor. So as you know that if this numerator part, once the P1 L1 change to P2 L2 means numerator part is increasing. So for the same denominator, like what I am telling is for this voltage, P1 L1 corresponds to this value and P2 for this voltage, this is here. So if you increase the numerator, then for P2 L2 at this point itself it will be higher. At this point also it will be higher. At this point it will also be higher. It will be higher. So what I mean that if you change the P and L, the nature of the conductor cost again inversely proportional to the V square. However, for each voltage, the associated cost will be higher, right? I hope that I have explained you. So now I have the formal slide for this. So if you have the different cases of real power to be transmitted and the distance, the product of P1 L1. You must remember that whenever I am saying that P2 L2 is greater than P1 L1, this may be that either due to higher P or due to higher L or due to both. So this will be the scenario. And what will be the insulator cost? Insulator cost will be the proportional to the voltage. So insulator cost will follow the same trend as in case of the single P and L. So insulator cost is right like this, and the conductor cost for the three different scenario of real power and the distance to be transported are different. Now in this case, try to get the total cost. Since the 3 and if already 4, and if I again draw the 3 total cost, then it will be the 7, and just in a single graph it will be much complex. So I have just drawn it for 2 cases only, and that I would like to show you. And just see that this blue dotted curve is the sum of this cost plus this cost, right? These two sum is here, and this orange dotted line is the sum of these two curves. Sorry, this conductor cost curve plus insulator. So these two sum here. I write you. This is the conductor cost for P1 L1 with respect to voltage, right? This is the conductor cost for P2 L2 with respect to voltage, and this is the insulation cost, insulator cost with respect to voltage. So it is not going to change with either changing in the power or distance. It is the insulator cost always depends only on the voltage, so it is again the same. So the total cost for the conductor plus the insulator in case of P1 L1 is represented by this blue dotted line, and in case the total cost for the conductor and the insulator in case of P2 L2 is represented by this. As you can see now that the most economical voltage is changing. The most economical voltage is changing. For P1 L1 case, the most economical voltage is somewhere here. This is the most economical VE1. And for case of P2L2, most economical voltage is somewhere here. I think this one. After or this one, because after that it is increasing. So this is BE2. What does it mean? As the product of power and distance to be transmitted is higher, or either the power to be transmitted is higher or the distance to be transmitted is higher, the most economical voltage also becoming higher, right? Very clear. So for higher power or distance to be transmitted, no, okay, just I will go back. I will explain one more thing. So this is now just in this curve, say for the VE1, what's the, this is the total cost. This is the total cost. Now, if we see for the, what happened? What happened? Okay, we are so just consider the most economical case voltage here. In this case, what is the insulator cost? Insulator cost is this much, right? And what is the conductor cost? This much, right? So
सर
this is the
हजुरको स्क्रिन
conductor cost for
सर स्क्रिन सेयर भइरहेको छ
हजुर
हजुरको स्क्रिन सेयर भइरहेको
के
छैन जस्तो लाग्यो
के भइरहेको छैन
स्क्रिन सेयर भएको छैन जस्तो लाग्यो सर अहिले भर्खरै
स्लाइड भएन
हजुर सर
भयो अहिले भयो
छैन
भयो कि नै छैन
अहिले क्यामेरा नै आइरहेको छ सर तपाईँको
हजुर
क्यामेराबाट नै देखिरहेको छ सर
हो र
हजुर
अहिले एकछिन के प्रब्लम भयो त्यो मैले गरेँ एकछिन म फेरि है
त्यही बाटो नै
देखिया छ
हजुर सर अब आयो
आएछ
हजुर
है यहीँ थियो यहाँसम्म त अघि त आएको थियो होइन अघिसम्म त आएको थियो
हजुर सर त्यो बिचमा ब्ल्याक स्क्रिन आएपछि चाहिँ गएको
ए यो दुईटा त भइसकेको थियो होइन यो दुईटामा त प्रब्लम थिएन फर्स्ट यो र यो
हजुर सर
यो
भइसक्यो
यो एक्सप्लेन भएको थियो यो भएको थियो होइन यसमा हो होइन ओके सो आई विल एक्सप्लेन ओके एउटा कुरा यसमा म अझै ल एकदम क्लियरली बुझाउँछु यो डटेड लाइन जुन ब्लूको डटेड लाइन छ यो भनेको कन्डक्टर कस्ट फर P1 L1 प्लस इन्सुलेटर कस्ट रिप्रेजेन्ट गर्छ र यो अरेन्जको डटेड लाइन यो कन्डक्टर कस्ट फर P2 L2 र त्यसैको इन्सुलेटर कस्टलाई रिप्रेजेन्ट गर्छ होइन हामी त्यो कुरा गर्यौँ र हामीले हेर्यौँ कि इकोनोमिकल भोल्टेज जुन द्याट इज जसमा कस्ट जुन पोइन्ट जुन भोल्टेजको करस्पोन्डिङ टोटल कस्ट मिनिमम हुन्छ यो चाहिँ प्यारी भइरहेछ when the power and distance to be transmitted is lower the economical voltage is also lower if the power and the distance to be transmitted is higher in that case the economical voltage is also higher so that was the first observation now go even more minutely in case of just say the first case when the P1 L1 we have to be transmitted then the insulator cost is this much this is the insulator cost for case 1 and this is the conductor cost right now if we go for this case this is the conductor cost and this is the insulator cost case 1 now if we go for the case 2 then for case 2 the insulator cost is this much that is the with respect to the previous one the insulator cost is in case 2 is higher than case 1 and this is obvious because the economical voltage itself is higher so this is the insulator cost and what is the conductor cost in this if we see this is the conductor cost in that case and that conductor cost if you plot is also higher with respect to the conductor cost for case 1 what does it mean why I'm talking this is if your power or distance to be transmitted is higher not only the most economical voltage is higher but also the per unit length conductor cost is higher what does it mean that when the conductor cost is higher once the size of the conductor becomes higher so just very important conclusion I am telling you from this is high voltage lines whenever we say high voltage lines for a optimum design line the high voltage lines have higher size conductor as well. In the last class I had, when I started, then I had told you that whenever I ask somebody that why we go for higher voltage, then they reply me usually that, sir, if we go for the same power, if we go for higher voltage, the current will be lesser. Or current will be lesser means we can use the lower size conductor. So yes, of course that is correct. But for, for the most economical design, what is happening is that if you are transmitting more, when you are going for higher voltage, they are using the higher size conductor as well. What does that mean? Again, I repeat in very simple language. That is, the conductor size usually we choose for 11 kV. Say for we have 11 kV. 11 kV. We use usually that's a 95 mm square conductor. That usually the highest size conductor used for 11 kV is called the dog conductor. I don't know whether you know the name of the conductors or not. This is the highest size conductor used usually for 11 kV. But for 132 kV or 220 kV, whatever we say, this may be the lowest size conductor. The higher size conductor may be have the size of 200 mm square or 400 mm square. So what does it mean? That as we go for higher and higher voltage lines, the conductor sizes are also higher. It's not, don't confuse that going for higher voltage, the size of the conductor is lower. And why this is? Because the power to be, for higher voltage we go only in the case when the power to be transmitted is higher. So high power transmitted case, both the voltage and the current is higher, not only voltage. Okay. So in summary, what we can say that why we do not go for the, in each and every case is the high voltage, because the high voltage lines are potentially economical but have a, and also have a high capacity. Just I give you a very informal example. Suppose you have to transport 100 tons of some material from one place to another, and you have to transport 5 kg from one place to another. You have the choices of either hiring the train or hiring the truck or hiring a taxi. Obviously, you know that the per unit transportation cost is least in case of train, per unit transportation cost is highest for taxi. But if you have to transmit only 5 kg or 50 kg of some material, it is not wiser to hire a train for that purpose. It's better to transport it by taxi. It is economical. Same thing apply for the transmission line design as well. Per unit cost for, that is for per unit power to be transmitted, per unit power I'm telling, per unit power to be transmitted cost is lower for high voltage lines. But these high voltage lines have higher capacity. These are economical only if you have to transmit very high amount of power. For the lower amount of power, per megawatt cost, transportation cost is higher. But still, we use the lower voltage case. Yes, these are just, we are considering the economical aspects of the line. Now, sometimes the higher voltage may be needed just not only for the purpose of economy, but maybe for the technical purpose. What is that scenario? Just I will explain. Suppose again we have a line. Say this is the sending in voltage. This is the receiving in voltage. This P again, P amount of power is transmitting here. The transmission line have both the resistance as well as inductance. But sometimes for the ease in calculations, accept the loss. If you calculate the loss itself, you must consider the resistance R. But for other purpose, often in the transmission line analysis particularly, if this R by X is very small, is very less, then we may neglect this R because impedance is R square plus X square root under. Now suppose both are 1 and 1. In that case, both is meaningful, isn't it? Because its square root will be, this Z is coming to be 1.41. But now suppose this X is 1 and this R is 0.1. Now square it both individually and add it. What will be it? This Z is almost 1. So even less by 1.1. So that means if we add 0.1 square plus 1 square and square root, 0.1 square, and then it is coming 1.01 square root and is virtually 1. Right? So, but if we are calculating the real power loss itself, we cannot neglect R. But for other purpose like voltage drop and other analysis, we often neglect this R. And then we model the line simply by the reactance and we call it the lossless line. So for a lossless line, if we, because I could have go with the R this also, but it would be difficult at this stage to explain. Uh, that's why I'm considering a lossless line, and I would like to just recall your one expression what you have. You know that whenever you have this Vs and Vr, they in AC system, these are this power voltage and are not only the in magnitude but have the phase as well. So this may be this Vr and this Vs are the phasor quantities, and this is the reactance, total reactance X, which is nothing but per unit length reactance into the L, where L is the length to be transmitted. And if this P is, now this phasor voltage may be expressed as one of the phasor you need to take the reference, as you know. Then this is VR magnitude 0, then this Vs magnitude delta. We usually write this. Now, I hope that you might remember, if you try to express the correlation between this Vs, Vr, and this P, then you might remember a very popular power transfer equations for a lossless line is P is equal to Vs VR upon total X inductive reactance of the line of in and the sine delta, where this delta is the angular difference, phase angle difference between the two end voltage. This Vs and Vr now are the only the magnitude of the voltage at the two end, and this X is the total reactance of the line. I hope that you remember it very well. This X, sometimes we may write it like per unit length reactance into the line length. So that means I am telling that this reactance is increasing if the line length is longer. Now, you know that this delta is also called the power angle. This delta we cannot, from this expression itself, it's very clear that for a given line, Vs, Vr, X, L are fixed. In that case, as you are go on increasing the P, the delta goes on increasing. But we cannot go this phase angle difference beyond a certain limit. And that you have studied in the power system stability. In the power system stability, you have studied that if the power angle difference, initial power angle difference before the disturbance is lower, then the chances of transient stability is higher. And that limit, I remember that you might have been taught that around 30 degrees. So this delta has a certain limit. Once we put this delta as the limit, it causes the limit in the P. Again, I would like to clear your confusions. When we say that the phase angle limitation, phase angle difference limitation for the transient stability is 30 degree, this does not mean that if your phase angle difference for in some cases in between the two buses in the power system is 35 degree, then the system will go in unstable. No, this does not mean that. It means that lower will be the phase angle, higher is the probability of remaining the system in synchronization even after a big disturbance. And from the the practical speed of the relay, circuit breaker, voltage regulators, it has been fixed that if this phase angle difference is around 30 degree, then the chances to remains in synchronism in case of transient disturbances is higher. So, but just right now, we just say that if we fix this delta as the limit, then there will be a limit in the P. So, if this we put the sine delta as 30 degree, then the sine delta is about 0.5 for delta limit as 30 degree. And I write it as this equation 0.5 X and L. And this is the P limit. Okay. This is the sending in and the receiving in voltage. And you know that the Vs and Vr is not varying. It's not that sending in voltage is 100 and receiving in voltage is just 1. If this is 100, this may be 90 or 95 or maybe 100, something like that, or 105. So what does that mean? That the Vs and Vr is almost in the same, and since right now we have not computed that how much will be the voltage drop in a particular line or something, so in terms of rated voltage we can say that this Vs and Vr is in the close proximity to the rated voltage of the line, and just I say this, that's why, as Vs square. So even I can remove this 0.5 and just say that P limit is proportional to some constant into V square upon X L, right? Now, let's talk about what is this X. I hope that this inductive reactance, this is of course, I am writing separately the small x and L together, means separately, because I am telling this X is the inductive reactance per unit length. So this X is nothing but 2 pi F into the inductance per unit length. This L is inductance per unit length of the line. I hope that in the power system 1, you have calculated the inductance expressions for so many varying cases, and that expression L was 2 into 10 to the power minus 7 ln GMD upon GMR in Henry per meter, right? Now, what is this GMD and GMR? I hope that you know this. Just I would like to remind you that this GMD depends upon the spacing of the conductors with respect to ground or with respect to each other. So that means phase spacing. It depends on higher the will be the phase spacing, more will be the GMD. And this GMR is mainly depends on the size of the conductor. So that means it depends on the radius, something correlated with the radius of the conductor. GMR will be higher if the size of the conductor or cross-sectional area or radius of the conductor is larger, and vice versa. This phase spacing, by now you might be have some idea that ultimately depends on the voltage. Higher will be the voltage, more will be the phase spacing, and ultimately more will be the GMD. So always it's true that GMD for 132 kV line will always will be greater than 11 kV because it has higher voltage, having higher spacing between the conductors. GMR, if the size of the conductor is higher, it will be higher. Now, just in 2 slides before, we have got a very important conclusion. And if you recall that, what I have told you is, I had told you that if this voltage is higher, usually the size of the conductor is also higher. Means the numerator and denominator in this expression increases or decreases usually together. So that means it's not that GMD is varying from 1 to 100 times. First of all, that itself is not practical. Say 1 to 10 times, and GMR is reducing. So that means this changing, it is there. It might be the case that GMD is changing, say, from 1 to 10, and GMR is changing from 0.1 to 0.0001. No. If this changing 1 to 10 means this is also somehow, at least it will be higher from 0.1. It will not be lower than that. That I mean. So both are increasing almost together. And I would like to inform you that this GMD upon GMR for all practical lines starting from transmission to distribution is varying in the range of 400 to 1200. Why I am telling like this does not mean that when I am saying that once GMD is increasing for practical line, GMR is also increasing. This does not mean that proportionally. Yes, only if increase, this also increase. So in some cases, this increase bit higher, this lower, and so on. So if for all practical transmission line, this GMD upon GMR ratio varies in the range of 400 to 1200. Now, if just we put this in this expression, what you will get is, okay, I have deleted, so I write here somewhere the P limit expressions we are discussing was V square, some constant B square upon a small x into L. Okay, this I had deleted mistakenly. So 400 to 1200. Now take the ln of 400. If you calculate this for 400 case, for 400 case, it is around 0.6. And if you calculate the same for around 1200 case, it is around 0.7. So what does it mean? That inductive reactance, if you just multiply this quantity by this or this and this, the inductive reactance for all practical lines, for practical lines varies varies in between 1.2 millihenry to 1.4 millihenry. No variation, not much variation. You have taken so many cases, stranded conductor, solid conductor, bundled conductor, and so on. So now you might have been. So even assuming it as a fixed quantity, inductance, if you cannot calculate, is not a big deal. Now you might have the row teachers have made me the fool. They have given one full chapter, so many cases for inductance calculation. Why we need to calculate it? So if you don't have any idea, if you don't have any idea about how much would have been the inductance for a particular line, just assume around 1 millihenry. It will be sufficient. It will be accurate. It do not vary that for some transmission line case per unit length reactance is 1 henry and for other is 1 millihenry. No, it varies in very narrow range, right? So with this, what I want to convey you is, so this I have just discussed with you. And so for practical lines, the value of per unit length reactance vary in narrow range. So this is very narrow and this has already limit. So what does it mean? That we can say that P limit is proportional to V square upon L, right? So this L is the line length to be transported and this is the voltage. If we like to plot this in a curve, then we get that if we plot x-axis in the as a line length and y-axis as the power handling capacity for a fixed voltage, that means voltage is fixed, then the power handling capacity or power transfer capability of the line at a given voltage goes on decreasing as the line length goes on increasing. So if you say that your line length is just here is the 100 kilometer, you have the power transfer capability of this much power, P limit or P limit say for 100 kilometer line length, then say for 1,000 kilometer line, this P limit will be lower. This transmission line cannot carry at the same voltage the, the same amount of power. Now, why this is important is you have chosen a say voltage, you have chosen a conductor, then that line has the capacity of some power. So power transfer capability for a selected voltage and conductor from current carrying capacity point of view. Okay, the power handling capacity is not dependent on the power line. Say what I mean is you have selected the V, you have selected the cross sectional size of the conductor. Of that means it fixed the I limit. I limit has been fixed, and once V and I limit has been fixed, you can calculate P as some constant into V I limit. So this I limit is called why a particular conductor cannot carry more than value of conductor current is, after that it may fail. So how it fails? The heat generated may deteriorate its property or something like that. So that's why this I limit is called thermal limit. And in that case, this P is also becomes the thermal limit. And again, if you say plot it, say like this is the L and this is the P limit, then the thermal limit will be independent of the line length, isn't it? Because in this expression, we do not have any line length. It will be, so this is for given voltage for a fixed voltage and conductor size. Conductor size. Now the P again in the, if we plot the previous curve also in the same sheet, then the P limit due to transient stability depends on the line length. So as you can see from this curve, I have plotted it, that's why I'm deleting it. So this is the scenario. This is the thermal limit, which is independent of the line length, and this is this is the transient stability limit. So this is the transient stability limit. Now suppose you have P amount of power to be transmitted only over this distance L1. In that case, we have both the limit, thermal limit as well as stability limit. But which is dominating? Dominating is thermal limit. But if you have to transmit this L2 distance of the power, again the voltage is same conductor, but now again you have the two limit, this and this, but here the dominate at this stage, dominating factor is thermal limit. And for this case of line, if in this case where the line length is L2, the dominating factor for power transfer limit, of course, in both the case is transient stability limit. Now, from my point of view, if you ask me which is better, I will tell you, I will ask you that yes, here, though we had the capability of this much, but we have made the investment only for this. So no worry, no worry. This is okay, economically justified because I have investments of conductor material cost and voltage insulator cost, and that we are utilizing fully. But at this point, I have invested the conductor cost and voltage, which could have carry out this much amount of power, but due to transient stability limit, I have not been able to carry this much power, only this. So what would have been my desire is shift this curve so that either this is bigger above this or at least it should cross this. In that case, I can utilize my full investment in the conductor cost and the voltage. How we can do that is one of the method could be if we increase the voltage, increasing the voltage because this curve is V square by L. So we may have something like that. Increasing the voltage, you may say that yes, our thermal limit also increase. Yes, it will increase. It will increase. It may be something like this, right? It's still pressure, so we can use it. So one of the method, I will discuss this one by one again, even later part of the course. Just understand fundamentally. And you might have heard this sentence very often that for the lower length, the thermal limit is the criteria, whereas for long length, the limiting criteria is the transient stability. This is the fact. One of the method to increase the power transfer limit is to increase the voltage. So for different voltage, we have different here. Of course, as we go on increasing the voltage, the power transfer, even for now, we do not have other choice than if I have to transmit this much power, say this much power I have to transmit over this much distance, then whatever, whether it is economical or not, leave it. But I have no choice rather than using this voltage. If I use this voltage, I cannot do it. So this is the technical requirement. As I have written it as the one of the method, you may have been the query that what are the other methods then? So there are few methods by which we can increase the power handling capacity. One of the methods I say is called to reduce the line reactance. You may ask me the question, just immediately you have said that reactance cannot be reduced. And the P limit expression, if you recall, is equal to some constant upon B square upon a small x into L. And I have told you that this x is no choice. We cannot vary because this x is correlated with the line spacing and conductor size with the logarithm. And just to make this x half, you may have to reduce it 100 times the spacing, which is not possible, right? How we can reduce it is, one of the method is, say you have a line, so just put a series capacitor, for example. This is sending in and this is receiving it. Now, this is your X into L original. And if I put a series capacitor, one thing you remember, you might remember that this reactance, though I write it at this lump model, in fact, this reactance is throughout the line. This reactance is in fact not just concentrated at the center, but it is, but just to model it, I write it, I have written it in one place. Now, but if you put a capacitor somewhere, say this is the line length L, I put a capacitor at a distance of L by 2. That is just exactly at the middle. Exactly at the middle, I have put a capacitor having a capacitive reactance of XC. Does not look like capacitor. So this is the line reactance, and external capacitor I have put over here having the, then the total reactance of the line is X into L minus XC. And if you put this over here, and now suppose you have made the XC is equal to XL by half. Just one case, not always it should be half. If you put XC of series capacitor having the capacitive reactance of the half of the total line reactance, then you can see that your power transfer limit can be made double. Yes, it's very, looks like very simple. Why not to go for this, right? Oh, one of the method is the series compensation, just I have told you, but it has many drawbacks. Like just one drawback I would like to make your attention. Now suppose line could have a short circuit anywhere. Suppose there is a short circuit at this point. There is a short circuit at this point. So say case one, a single line or three phase to ground fault, and there is this is case 2. What is the difference between case 1 and case 2 is, case 1, the fault occurs just immediately before this capacitor. And in case 2, the fault has occurred just immediately after the capacitor. So in first case, the fault current in case 1, IF, will be whatever is the voltage divided by XL by 2, because this is around middle of the line. This is a fault current. For case 2, I fault current is V upon XL by 2 minus XC. And unfortunately, if we choose this XC as XL by 2, half of the reactance, as I've given you the example in the previous case, then how much will be this quantity? This is 0. And the fault current ideally become infinity. In fact, it will be limited by some resistance of the line. So it will not be infinity, but very high. So it's dangerous. Not only dangerous that very high current flow through this high current will create the voltage drop across this capacitor so high, because this fault current in case 2 has to flow through this capacitor, and the voltage build up across this capacitor is so high that this capacitor may damage. There are methods to overcome these situations, but what I just want to threaten you, in a sense, very rough language if I use, or alarm you, that though the series capacitor has a capacity to increase the power handling capacity of the line, but it has some drawbacks as well. So what is done is, this choice is made only if we do not have other choices, no alternatives. So increasing the power transfer limit constrained by transit, so drawback, and hence used only if no other options. When is so during the design we could have the several options, so we do not prefer it. But now suppose I have already existing line, and previously the power flow through that line was smaller. Now, due to increase in the demand and generation penetration in the system, that line has now the power flow has to be increased. So for existing line case, we cannot go other options. We are not going to design it. So we may use a series capacitor with some countermeasures for the drawbacks, as I have just immediately explained you, and is used. Now, another alternative to reduce the line reactance could be go for multiple circuit. So previously I have given you example that we have a one line single circuit. Now suppose you have a double circuit. Whatever the inductive reactance I have told you about 1.2 millihenry or something like that per kilometer is for the single circuit line. So for double circuit, if you have double circuit, then it has the X, it has also X. So double circuit means the lines are connected in parallel. So its equivalent reactance is X by 2. So another method for the increasing the power transfer capability can be improved either going for higher voltage during the design or going for increase multiple number of circuits. So during the design, the voltage selection, whether to go for higher voltage, whether a single circuit higher voltage or relatively lower voltage with multiple circuit, is also a choice for the designer. I hope that, though I have few slides, but the time is. Do you have? Okay, sir. अहिले त अब शनिबार त आज क्लास छैन होला हैन? हेलो
हजुर सर
कि थाक्नु भयो
आजलाई यति गरौँ होला
आजलाई यति गरौँ सर
ल ल ठिक छ केही क्वेरीहरू छ केही छ क्वेरी हेलो
नो सर
छैन जस्तो देखियो
होइन त
okay then we meet now next on Monday हो